Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, merge k-sorted list. So basically we have k linked lists, and each linked list is already sorted in ascending order. What we want to do is merge all the linked lists into a single sorted one, and then return it, right? So for example, this is the representation of 3 linked lists, like this. And so to merge them, we have the smallest ones first, so 1, 1, and then 2. And then 3 from here, and then 4 from the first one, and from the second one, and then 5 and 6, right? So this one we end up with a sorted one. If it's empty, we just return empty. If it's also contains empty linked list, we just return empty. So we need to support empty linked lists. And the size of the linked list, it can be up to 10 to the power of 4 number of linked lists, and each linked list can go up to the length of 500, right? And the values also are in this boundary. So you can see it's a pretty long the number of linked lists can be pretty long, but the individual linked lists are not that long, right? So how can we solve this? Okay, so how do we solve this? Well, definitely the easiest way to solve it is, because a linked list is just complicated to handle, you could just convert all of these into lists, right? And then merge them together. So 1, 4, 5, and then 1, 3, 5, and then take 2, 6, and then merge all of these together, right? That way you get 1, 1, 2, 3. You will get it first unsorted, and then sorted, and then converted back to a linked list, right? That's definitely easy, but first of all, that means we will not take advantage of the fact that these are sorted. So that's the first downside. The other downside is also the extra space we'll be using to create a new list, right? So that's not an ideal solution. So how can we do better? Well, one thing we can do is we can definitely, for example, create a heap, put all the elements in a single heap, right? A min heap, for example, or right? So put all of the elements in that heap, and then just extract each time and create a linked list, okay? But that's still not ideal, because we are creating all of this extra space that contains all the elements, and we're also still not taking advantage of the fact that they are sorted, right? But this solution is pretty simple to do. Just basically add all the elements in the heap, and each time extract the smallest one, right? And create a new linked list out of that. Okay, so that's also not ideal in a similar way to the first solution. So how can we do it? Well, what we can do actually is create a heap and only add the k elements of the linked lists, right? And each time we pick an element that is the smallest, right, add the next element. What do I mean by that? That way our heap length is going to be just of length k. It's the extra space we are going to use is just O of k, instead of like the previous solution, it was going to be k multiplied by the length of each linked list. So let's pick the length of the maxed one is going to be n, right? But with this one, the extra space is going to be just O of k. So how do we do that? So let me run it on this example so we can see. So let's say our heap here, we can just have our heap. So these are the lists, these are the indices of where they are, okay? And so each time we'll just add the value and the index of the list. And so for example, first we'll just add the first ones, the first values. And so that would be, let me actually make it this bigger. So first we'll add just 1, and the index is 0, and 1, and the index is 1, and then 1, and then 2, and the index is 2. Right? So basically this is going to contain the value of the node and the index of the list. Okay? And now we pop the smallest element. Since it's a heap, it's going to be by the first element first, so, and then by the second element when they are equal. So since these are equal, we will pop off this one, which is 1, 0. And so we'll add 1 into the start of our linked list, right? And then what do we do? Well, when we add this, we should add the next one, because what if this one was 1 as well, right? Then this one should be taken before this 2. So if we don't add it, it won't be taken. 2 will be taken first. So we will need to add this one. So every time we pop, we take the index. So we say, okay, the list index is 0. So let's just pick that list and add its next value into our heap. And so we do that. Next value is 4. And the index is 0. Okay. And now we pop the next smallest element. What is the next smallest element? Well, the next smallest element is this one. And so we pop 1, 1. Okay. And so we add that one here. And now we do a list 1 dot next. We add it to the linked list. And so now we add to our linked list this value 3, right? So we added this, we added this, we added this. So we add 3. What's the index is 1. And so now we pop again from our heap the smallest element. What is the smallest element? It's this one, 2, 2. Okay, so we pop 2, 2. That means we add 2 here, and then we take the next of this index. So the index is 2, and we add it to our heap. We add always the value in the index, and so here we add the value which is 6. So it's going to be 6, and the index in the list is 2. So the only reason we are adding the index is so that each time we go to the next element. This, if you think about it, this is similar to what we do if we were merging two arrays, right? What we do is we take only the 2 first ones, right? And then we compare, we add the smallest one, and then we compare against the next value in the list we just used the value from, right? And so here, once we do that, now we pop the smallest element again. And so what is the smallest element here? It's 3, 1. And so we pop 3, 1. We add 3 here. And now we take the index to get the next. And so the index is 1. And so we go to 1 next. That's going to be 4. And so we add 4, index 1. And we pop the smallest again. What's the smallest? Between 4, 0 and 4, 1, the smallest is 4, 0. And so we pop 4, 0, right? And we add 4, and then 0. We take 0 dot next, which is going to be 5. So we add 5. We add 5, and the index is 0, right? And now when we do that here, we pop the smallest element again. What's the smallest element? It's 4, 1. So we add 4, and you get the idea. We can do the rest. And once a list is empty, if a list dot next is null, we shouldn't add it. We just skip it, right? That way we will just add the remaining elements of the rest of the list. Okay, and so that's the idea, and so that's the idea of this solution. Yeah, and it should be pretty fast. So let's implement it and make sure it passes our test cases. Okay, so let's implement the solution we just saw in the overview. So first, what we need to do is we need to create our heap that will contain the elements, right? And then after that, we will go for I lists in enumerate of lists. And then we are going to, if it's not null, because sometimes the list in our list may be empty, that's what the problem says, we are going to push the first element into the heap. And so the first element is going to be just list.val, right? And then we want to add the index of the list so that we can add the next element once we pop an element, right? And now we are going to do head is going to be equal to, this is just a trick here where we put a dummy node so that when we are returning, we'll just return head.next, right? Just so that we don't have to deal with the headache of the first element, right? So we are starting our current equal to head. And then we are going to do while heap, right? We are going to take a value and an index and do heap q, heap pop, and then pop from the heap, right? And then for current.next, so basically this extracts the smallest element and the index of the list. And so we want to add it to our linked list, right? And this current pointer just maintains the pointer on the last element added to our result linked list, right? Because you can see at the start, it gets assigned the head that we returned the next of. So we will return the first element of the linked list. So here we create a new node that has that value v, right? And then we want to go to the move our pointer, right? Because we just filled this one, we don't want to override it the next time, so we want to move our pointer to the next one. And now we want to add the next element, the next node of this I list at index I, we want to add it to the heap, right? That's what we did in the overview. And so we say lists I dot next. If this exists, right? Because sometimes maybe we reach the end of the list, then we add it to our heap, right? And so we say heap q dot heap push. We want to push the next element, right? So an easier way to do that is just to do lists I is equal to this, because we have to move the pointer anyway, so that next time we add the next of the next, right? And so here we just do this to the heap, and then we want to add list.val and the index of the list. So we add the next element basically with this. We add the next element to the heap. And now that's pretty much it, right? So let's run this. Looks good. Let's submit. And that passes our test cases. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.